For decades, scientists believed the Big Bang was the beginning of everything: time, space, and matter. But new data from the James Webb Telescope tells a different story. It found galaxies that are too old and too developed to fit inside our timeline. If what Webb saw is real, it means the universe might have existed long before Bang itself. This is the discovery that's rewriting the laws of how the cosmos was born. If you're interested in the unknown, subscribe and join the journey as we continue exploring the mysteries of the universe. When the James Webb Space Telescope began full operations in mid-2022, astronomers expected confirmation, not confrontation. The mission's goal seemed straightforward: look back to the universe's first few 100 million years and witness the birth of the earliest galaxies as they emerged from darkness. Webb's design made it unlike any telescope before it. Its gold-plated 6.5-meter primary mirror, made of 18 precisely aligned segments, collects more than 6 times the light of Hubble. The observatory orbits 1.5 million kilometers from Earth at a gravitationally balanced point known as L2, far from the planet's warmth and glare. From that stable perch, its instruments stay chilled below -230 degrees Celsius, allowing them to detect the faint infrared glow of the first stars whose light has been stretched by cosmic expansion. Because light travels at a finite speed, about 300,000 kilometers per second, every additional light year of distance represents another year of history. A telescope sensitive to faint infrared light is effectively a time machine. The farther it looks, the younger the universe it reveals. By capturing wavelengths invisible to the human eye, Webb peers more than 13 billion years into the past, approaching the moment when the first atoms condensed into suns and galaxies. According to the standard cosmological model, the universe began roughly 13.8 billion years ago in an extremely hot, dense state that has been expanding and cooling ever since. About 380,000 years after that beginning, the first atoms formed and the brilliant fog of plasma thinned, releasing the cosmic microwave background, a faint afterglow still detectable today. What followed was a long, starless interval, the so-called cosmic dark ages, filled only with hydrogen and helium gas drifting through space. Gravity slowly pulled matter together until the first stars ignited around 200 million years after that origin. Clusters of those stars merged into larger systems, and by 1 billion years, mature galaxies were expected to exist in significant numbers. Hubble's deepest images supported that timeline. Webb was designed to uncover the missing intermediate stages. Instead, its very first data forced scientists to rethink the script. In a patch of sky no larger than a grain of sand held at arm's length, an area chosen because it looked nearly empty, Webb's first deep field revealed thousands of galaxies packed together like cosmic embers. Some were chaotic smudges typical of youth, but others appeared bright, compact, and astonishingly massive. Their light had travelled more than 13 billion years, showing us a universe only a few 100 million years after time itself began. That level of organisation should have been impossible so soon after the first expansion. Simulations based on the lambda CDM model, lambda cold dark matter, predict that galaxies of comparable size need almost 1 billion years to grow. One of the most striking examples came from Webb's survey known as GLASS, the Grism Lens Amplified Survey from Space. It uncovered a compact system now called GLASS Z13, whose light began its journey around 13.5 billion years ago. Webb captured it as it appeared roughly 320 million years after the universe's birth, yet it already looked mature and luminous, possibly containing billions of stars. Soon afterward, another candidate, CEERS 93316, surfaced from a separate observing program, dating to roughly 240 million years after the first expansion. Even if later refinements adjust those numbers, the pattern remains unmistakable. Galaxies were forming at a pace that defies existing theory. To understand how extraordinary that is, remember how galaxies are built. The first generation of massive short-lived stars, known as Population 3, formed entirely from hydrogen and helium. When they exploded as supernovae, they seeded the surrounding gas with heavier elements. Those metals allowed the gas to cool more efficiently, collapsing into new stars and enabling the growth of the earliest galactic structures. But these cycles take time. Each generation must live, die, and recycle material for the next. Seeing chemically enriched, well-organized galaxies when the universe was still in its infancy implies that several generations of stars had already come and gone in rapid succession. Webb's near-spec spectrograph confirmed traces of oxygen, neon, and even carbon, elements that can exist only after multiple stellar lifetimes. The evidence pointed to a cosmos that achieved complexity far earlier than expected. Initially, some astronomers wondered whether Webb could be misled. Could these bright smudges be closer galaxies reddened by dust, giving the illusion of great distance? Could gravitational lensing, light bent and magnified by intervening clusters, be making ordinary galaxies appear extraordinary? Teams across the world recheck the data using independent pipelines and calibration methods. When the distinctive hydrogen emission lines were measured precisely, several of the targets proved undeniably ancient, more than 13 billion light-years away. The most distant confirmed system so far lies roughly 33 billion light-years from us in today's stretched-out universe, meaning we see it as it was just 330 million years after the first light of creation. More examples almost certainly await detection as Webb continues to scan deeper. If galaxies of that mass already existed, something in our understanding of cosmic growth is incomplete. The current model assumes that dark matter, the invisible substance making up about 85% of all matter, served as the gravitational framework on which ordinary gas condensed. Perhaps dark matter interacted more strongly or formed dense clumps sooner than expected. Another possibility is that early gas clouds cooled and collapsed with astonishing efficiency, converting much of their mass directly into stars. Webb's early data suggests star formation rates up to 100 times greater than those in the Milky Way today, so intense that whole galaxies might have flared briefly like fireworks before settling into calmer states. Even with these adjustments, the numbers remain challenging. Simulations must boost both the rate of matter collapse and the conversion of gas into stars by factors of 10 or more to reproduce what Webb observes. The simplest interpretation is that structure formed faster than predicted. The more radical idea is that our timeline itself might need revision. If the early rate of cosmic expansion differed even slightly from modern estimates, the link between distance and time would shift. But even generous corrections cannot close the gap entirely. Something fundamental appears to be missing from our equations of the early cosmos. Webb's findings also compress the era of rhionization, the transformation when ultraviolet light from the first stars stripped electrons from hydrogen atoms and made space transparent. Prior to Webb, this was thought to unfold between 500 and 900 million years after the universe's birth. Now, luminous galaxies shining much earlier imply that the process began as soon as 250 million years after the first expansion, leaving a remarkably short window between darkness and illumination. The cosmic dawn seems to have been less a gentle sunrise and more an explosion of light. The telescope's unmatched sensitivity revealed yet another puzzle, evidence for supermassive black holes already in place at these early epochs. Some of the compact radiant sources Webb detects may host central black holes millions or even billions of times the Sun's mass. Growing such giants in only a few 100 million years demands either extreme feeding of gas or the direct collapse of immense primordial clouds, processes that strain the limits of modern astrophysics. Understanding how these ancient monsters formed has become one of Webb's defining objectives. To verify this emerging picture, astronomers are extending Webb's deep field campaigns and launching specialized programs such as Cosmos Webb, Jade's Deep, and Primer. These surveys will map immense regions of the sky, tracing how the first galaxies clustered, merged, and evolved. At the same time, theorists are re-examining assumptions about dark matter, gas cooling, and cosmic expansion, building new simulations to test each possibility. Within a few years, Webb's expanding archive should reveal whether these discoveries mark a statistical outlier or a profound shift in our understanding of how the universe built itself from chaos. What we know for certain is simple yet profound. The infant cosmos was not the quiet, slowly evolving realm scientists once imagined. It was crowded, luminous, and astonishingly dynamic, almost from the start. Galaxies grew sooner, stars ignited earlier, and black holes appeared long before anyone thought possible. Every new image from James Webb deepens the mystery and reminds us that the first light of creation still has secrets to tell. As more Webb data poured in, the pattern became undeniable. Independent research teams using programs such as JWST confirmed that the early universe contained far more large, bright galaxies than expected. Even after reanalyzing a few that proved closer than first thought, many remained astonishingly ancient. The statistics revealed that massive galaxies were 10 to 100 times more common in the young universe than any model had forecast, a discrepancy that cannot be dismissed as observational error. Simulations still cannot reproduce that speed of growth. Even when scientists raise star formation efficiency in their models, the galaxies remain too faint. To match Webb's data, gas clouds would have to collapse with near-perfect efficiency, converting most of their mass directly into stars, something no known process achieves. Some researchers suspect the key may lie in dark matter, which forms the invisible scaffolding that normal matter follows. If clumped together earlier or more densely than expected, it could have accelerated the gravitational collapse of gas. A small change in how dark matter interacts with itself or with radiation could have enormous consequences for galaxy formation. Several new models are now being tested using Webb's early data as a benchmark. Another possible factor involves the universe's expansion history. A galaxy's age is inferred from how much its light has been stretched as space expands. If that early expansion wasn't perfectly steady, our distance and time calculations could be slightly off. A faster early expansion would make galaxies appear older than they really are, a possibility linked to the Hubble tension, the long-standing mismatch between expansion rates measured nearby and those inferred from early universe observations. Webb's results may hold the clues to resolving that conflict. Still, even generous adjustments to the expansion rate cannot fully solve the mystery. Some of Webb's galaxies are simply too massive for the time available, no matter how the numbers are tuned. That's why astronomers are testing more radical ideas: modified gravity, exotic forms of dark matter, or new physics governing the behavior of matter under extreme conditions. These efforts don't discard the Big Bang, but aim to refine our understanding of what followed it. Webb's images also hint at supermassive black holes forming astonishingly early. Several compact, intensely bright sources show light patterns consistent with black holes millions or billions of times the mass of the Sun. The timeline leaves little room for them to grow from smaller stellar remnants, suggesting they formed directly from collapsing clouds of primordial gas. This direct collapse model could explain how massive black holes appeared so quickly and helped galaxies form around them. These early galaxies may also have played a central role in reionization. the moment when ultraviolet light from the first stars stripped electrons from hydrogen atoms, making the universe transparent. Webb's data show that this process may have begun hundreds of millions of years earlier than thought, shortening the cosmic dark ages dramatically. Together, these findings portray a universe that organized itself faster and more efficiently than any model allows. The balance between gravity, gas, and radiation must have been different, perhaps tuned by conditions we haven't yet measured. The early cosmos seems denser, more turbulent, and more active than ever imagined. Webb's spectrographs will now analyze the light from these galaxies in detail, measuring their true composition and motion. If confirmed, the paradox will remain. The universe built its first complex structures faster than current physics allows. That's the challenge Webb has presented to cosmology. It hasn't disproved the Big Bang, but revealed that the period immediately after it was more violent, efficient, and complex than anyone imagined. If Webb's revelations continue to stand the test of scrutiny, they suggest that the early cosmos was far more intricate than any theory so far imagined. Its images of luminous, well-structured galaxies crowding the first few 100 million years of existence defy expectations not just in scale, but in principle. They call into question the physics of how matter, energy, and even time first organized themselves into the universe we see today. One of the most immediate puzzles centers on dark matter, the unseen substance that shapes the cosmic web. In conventional simulations, it behaves like a cold, passive scaffolding that slowly gathers normal matter through gravity alone. But the galaxies that Webb sees appear too quickly formed for that slow choreography. Some physicists now explore models where dark matter is self-interacting, able to nudge or collide with itself and form dense clumps that draw in gas far faster. Others favour fuzzy dark matter, whose particles are so light and wave-like that they blur together, creating quantum pressure that subtly alters how structures grow. A few even speculate that it might have temporary interactions with radiation in the young universe, igniting earlier gravitational collapse. Each idea demands changes to particle physics, and each would make the universe far more dynamic than the quiet framework described in textbooks. Another possible key lies in the initial conditions of the cosmos. During the burst of inflation that expanded space in the first fractions of a second, tiny quantum fluctuations were stretched to cosmic scales. If those ripples were stronger or more uneven than assumed, matter could have gathered almost instantly into deep gravitational wells. New inflationary models, some inspired by string theory, others by quantum field interactions, predict exactly that. A rougher, lumpier beginning that would make Webb's fast-forming galaxies inevitable rather than anomalous. Then there are primordial black holes, theoretical relics of extreme density fluctuations that might have formed before the first atoms existed. If even a small population of these black holes emerged, they could have acted as seeds for galaxies, attracting gas and triggering cascades of star formation. Their gravitational pull would heat in falling material, producing radiation bright enough for Webb to detect across billions of light years. Intriguingly, some of the compact ultra-luminous sources in Webb's deep field images show exactly the kind of spectral fingerprints expected from these objects. Detecting a clear signature, perhaps a specific X-ray glow or gravitational wave pattern, would be one of the most profound discoveries in cosmology, linking the universe's first instance to the massive structures we see today. Webb's spectroscopy is also opening a new window on early cosmic chemistry. In galaxies less than 500 million years old, astronomers are already finding the spectral imprints of oxygen, nitrogen, magnesium, and even hints of silicon. Such elements can exist only after multiple generations of massive stars have lived and died. This means that the first stellar populations must have formed extraordinarily quickly, perhaps within 100 million years of the universe's origin. Some simulations suggest that these earlier stars were supermassive, hundreds of times the Sun's mass, burning furiously and collapsing into black holes after only a few million years. Their explosions would have flooded nearby gas with heavy elements, enabling the next generation of stars to form at breathtaking speed. Others envision violent mergers between nascent galaxies, where colliding clouds compressed gas to ignite intense starbursts. Either scenario paints the young cosmos as a place of chaos and creation happening simultaneously, a cosmic furnace rather than a gentle dawn. Equally transformative is Webb's evidence for a deep link between galaxies and supermassive black holes. In the modern universe, black holes grow at the hearts of mature galaxies over billions of years. But Webb is showing that this relationship may have begun far earlier. Some young galaxies already contain central black holes millions or billions of times the Sun's mass. The radiation from these active centers could have stirred, compressed, and regulated surrounding gas, influencing how stars formed. In this feedback loop, galaxies and their central black holes evolve together, an intimate partnership that may have shaped the entire cosmic landscape. These clues ripple outward to challenge our understanding of dark energy, the mysterious force accelerating cosmic expansion. If structures formed earlier and faster than expected, perhaps the tug-of-war between gravity and expansion was different in the past. Some cosmologists propose that dark energy's strength has changed over time, starting weak and growing stronger only after the universe reached a certain age. Others think the geometry of space itself may not be perfectly uniform. That subtle curvature could alter our measurements of distance and time. Webb's ongoing surveys, which chart how galaxies cluster at different epochs, could reveal whether dark energy is truly constant or an evolving phenomenon. Beyond that lies the most elusive question of all: what was time like at the beginning? Near the universe's origin, the known laws of physics merge into a domain where quantum mechanics and gravity coexist. Some theorists propose that time itself thickened as the universe expanded, flowing differently in its first moments than it does now. Under those conditions, what we measure as 300 million years could have passed in a fraction of that duration according to the universe's own clock. Others go further, suggesting that our universe may have bounced from a previous one. In that view, an earlier cosmos collapsed under its own gravity, compressed into a state of maximum density, and then rebounded, leaving faint imprints, density patterns that became the galaxies Webb now observes. If any trace of such a pre-existing cycle can be found in Webb's data, it would change our definition of a cosmic beginning itself. To explore these frontiers, astronomers are developing an entirely new generation of analytic tools. Sophisticated algorithms now trace every photon recorded by Webb, reconstructing the path of light across expanding space to infer how galaxies evolved chemically and dynamically. Machine learning systems compare thousands of simulated universes with real observations, searching for which physical laws best reproduce what Webb sees. On the theoretical side, cosmologists are blending quantum gravity mathematics with large-scale simulations, attempting to bridge the gap between the smallest particles and the largest structures. Complementary observatories are joining the effort. Radio telescopes such as LOFAR in Europe and the upcoming Square Kilometre Array in Australia will map the faint 21 centimetre signal of neutral hydrogen, charting how the cosmic fog lifted during reionization. The CMB Stage 4 experiment in the United States will remeasure the ancient microwave background with unprecedented precision, checking whether tiny irregularities match the galaxies Webb detects. Even gravitational wave detectors like LISA, scheduled for the 2030s, may pick up the background hum of primordial black holes or early mergers that helped shape the first galaxies, each new instrument adds another piece to the puzzle. Webb may have provided the spark, but together these observatories could illuminate the full chain of cause and effect from the universe's first instance to the vast structures we inhabit today. Step by step, they will reveal whether the cosmos truly evolved faster than theory allows, or whether we are glimpsing a deeper layer of physics woven into the fabric of reality itself. Whatever the final answers, one fact already stands beyond dispute. The young universe was astonishingly alive. It was turbulent yet organized, chaotic yet creative, a place where gravity, radiation, and matter cooperated to build complexity almost overnight. The James Webb Space Telescope has not merely extended our vision into the past, it has opened a doorway into a realm where the familiar laws of nature begin to blur, reminding us that the story of creation is still being written, photon by photon. The James Webb Space Telescope has done more than expand our vision of space. It has transformed how we think about time. In just a few years, it has shown that the infant cosmos was not a quiet nursery, but a storm of creation where light, matter, and gravity dance together in astonishing harmony. Each new discovery challenges the boundaries of what we thought possible, forcing science to rewrite its oldest stories. Now the race is on to interpret what Webb has revealed. Its data archive, already petabytes deep, has become a treasure map for cosmologists and physicists alike. New algorithms are being trained to read that map, searching for patterns hidden beyond human sight. Dim galaxies lost in the noise, strange colour signatures that hint at unknown chemistry, and distortions that may betray the presence of invisible matter. Artificial intelligence has begun finding objects so faint that they stretch the limits of what Webb itself can detect, suggesting that the early universe may be even busier than our instruments can yet confirm. The next generation of space observatories is preparing to take the handoff. The Nancy Grace Roman Space Telescope, launching later this decade, will scan vast regions of sky to measure cosmic structure on a grand scale. The Habitable Worlds Observatory, still in its design phase, will extend Webb's legacy from galaxies to exoplanets, studying worlds that orbit distant suns in search of chemical signs of life. Further ahead, mission planners envision telescopes cooled by liquid helium or shaded by kilometre-wide light-blocking sails, capable of capturing even longer wavelengths from the first molecular clouds. While Webb peers outward, physicists are looking inward, to the universe's hidden architecture. Experiments deep underground, such as Elux Zeppelin in South Dakota and Xenont in Italy, are hunting for the elusive particles that might make up dark matter. Others, like DESI and Euclid, are mapping how galaxies move today, testing whether the laws of gravity themselves may evolve across cosmic time. Together, these projects form a bridge between the largest and smallest scales, joining astrophysics with particle physics in the search for a single, unified picture of reality. But Webb's impact reaches beyond laboratories and equations. It has reignited a question as old as humanity. Why is there structure at all? If the universe organized itself so swiftly, perhaps creation is not rare. Perhaps it is what the cosmos naturally does. Some researchers are exploring the idea of universal self-organization, where complexity arises spontaneously whenever energy flows through matter, whether in galaxies, storms, or living cells. In that sense, the same principles that shaped the first stars may still echo in the chemistry of life and the firing of human thought. Each photon Webb captures is a whisper from a time before there were eyes to see or minds to wonder. Those faint signals travelled billions of years to reach us, carrying memories of a cosmos that was young, hot, and brimming with possibility. When we study them, we're not just observing ancient galaxies, we're reading the preface to our own existence. As Webb continues its mission, humanity stands at the edge of a new kind of science, one that blends observation, simulation, and imagination. Future telescopes will push even further, perhaps revealing the transition between nothing and something, the moment when the universe first learned to create. Until then, every new image Webb sends home reminds us that the darkness between stars is not emptiness, but history waiting to be understood. The telescope's mirror may hang far beyond Earth, but what it reflects is deeply human: curiosity, persistence, and the hunger to know where everything really began. If you've enjoyed this journey into the universe's earliest light, don't forget to leave a like and subscribe. It helps this exploration reach more curious minds. Thank you for watching. The story of the cosmos is still unfolding, and together we're just beginning to read the next page.